You can have a copy of everything. You don't have to take real good notes unless you want to. The seminar on improving reliability and safety performance of solenoid valves was prepared by Lauren Stewart. Unfortunately, she's not well and not able to present today. And although you would have a much more pleasant voice, I'm sure, Lauren should be given the credit for developing this excellent seminar. My name is Bill Goebel. I was somewhat involved in the research behind all of this, so I should be able to answer most of your questions. Both Lauren and myself work for exida. Exida is a global corporation, offices around the world. We focus on functional safety and cybersecurity. A lot of our people are former product development people. Many of our people are experts in functional safety certification, and we have a lot of people who are very oriented toward systems design, primarily in the chemical, petrochemical industries. And we all get together and fight and argue and come up with some really nice ideas and some nice products. exida does consulting. We have a group that is an accredited certification body. We do a lot of training. We have engineering tools, reference materials, databases, which we will be talking about to a certain extent this afternoon. And we have a professional certification program for professional competency. exida does spend a lot of our time on engineering tools. In particular, we have a full suite of safety lifecycle tools. These tools are meant to make the safety lifecycle cost-effective, primarily for owner-operators. At exida, we do a lot of research into failure rate data. All of our research is compiled and published in publicly available books. All of our methods for analysis, all of our safety lifecycle procedures are published in publicly available books, and we're quite proud that we have authored a strong majority of all the industry references for automation safety and reliability. Now, with the little commercial out of the way, let's talk about improving reliability and safety performance of solenoid valves. We've had some very interesting research in the last year, and it's fun to discover and improve on failure and reliability models. And we're going to tell you a little bit about that research this afternoon. We're going to talk about mechanical failure rates in general, cycle testing, and cycle test scaling. We're going to talk about a phenomena which has been researched pretty heavily by Lauren called stiction. The evidence of stiction, how it works, and then what we realized about the ways of improving solenoid valve testing and the implications of that. And lastly, we'll talk a little bit about recommended best practices in terms of final element design. Traditionally, mechanical component failure rates have been determined by a technique called cycle testing. The other technique that has been developed in recent years, primarily by exida, is called FMEDA, Failure Mode Effect and Diagnostic Analysis. Now, that's a technique that looks in detail at the design of a particular mechanical device, and knowing the failure rates of the components in the particular application environment, we can predict the failure rate of a brand new design long before field failure data is available. One of the nice things about FMEDA is that it can be used for low demand applications, which is appropriate for the process industries. But what about this cycle testing? Cycle testing is absolutely a valid technique used to estimate failure rates in dynamic applications. Now, the process industries, that's a high demand or even a continuous demand operation where the mechanical components are constantly or frequently moving. Now, there's a valid assumption involved in obtaining failure rate from cycle testing, and that is that premature wear out is the dominant failure mechanism during useful life, and that no other failure mechanisms are significant. Now, this makes perfect sense in a dynamic application when, in fact, the emphasis in mechanical reliability engineering for decades has been wear out. That is the cause of most mechanical failures. It certainly seems to be the cause of failures in my automobile. At least that's what my mechanic tells me. So this is a valid technique, and at Exida we use all of these techniques, but there's an issue. How do you calculate failure rates? Well, a cycle test is done on a set of products, typically a set of products quantity greater than 20 until 10% of the units fail. And you count the unit cycles, an average number of cycles per unit, and that is called the B10 point. B10, 10% of the failures. Okay, I understand why they call it that. And if you look in standards, for example, from the ISO 13849 standard, you'll see they publish typical B10 points. And you can see at the top of the list they have a B10 point of 20 million cycles, or maybe in some cases 400,000 cycles. And you can use this quantity of cycles to calculate a failure rate. Now, you do that by taking the number of B10 cycles and converting it to a time period by knowing the cycles per time period in any particular application. For example, let's say you're running 10 cycles per hour. You just count the number of, take the number of cycles until failure, divide by 10, and you have the number of hours until failure. It kind of makes sense. It's very logical. Then, a failure rate is calculated by dividing the 10% failure count by the time period. Now, this metric, the time period, is therefore very, very important. And there are some limitations. The real question is, of course, at Exida we wanted to understand those limitations because as a certification body, we are frequently asked to do cycle test evaluation. And many certification bodies use cycle test evaluation to provide functional safety certifications. To me, this is quite appropriate for machine safety where you have very dynamic operation. But I'm not so sure. There are real limitations. In fact, the certificates that you see often state the limitations assumed. In this particular certificate, the analyst assumed 10 demands per year, or 870 hours per cycle. One must ask, however, what time period is valid? Is it really valid to go 870 hours per cycle? Well, we started studying that because, in fact, the failure rate is calculated by dividing the failure count by the time period. What time period can we go? How far can we take this? Can we say 1 cycle per year, in which case a mechanical component sits without moving for a whole year? Well, why not? Maybe it's 1 month, maybe it's 1 week, but in order to use the cycle test method, we really need to understand the answer to one important question. How long can a device with a seal remain motionless before other failure mechanisms become significant, such that premature wear out no longer dominates? You see what we're trying to ask? We need to know How far can we take this? And we began researching it, and we came up with this term, this phenomena called stiction. And basically the words comes from the word static friction. Now you can read the definition. It's a force, a resistance to the start of motion. I remember things seemed to be stuck. I remember setting a wet glass down on my kitchen table, and of course I could push the glass quickly and easily slide that glass across the table, but I let it sit there all night. The next morning I came in, went to pick it up, and it was stuck. What's going on here? I once went to a refinery in western United States, and we were interviewing the people there about their experiences with final element failure rates, valves, actuators, solenoid valves, gathering up some field failure data. And one engineer told me, "You see that valve out there?" And I looked out. Yeah, it was a hand valve. And he said, "If I don't go out there and turn that valve every single week, no one will ever be able to move that valve again." I thought, why? Just don't know. No, we're not going to take it out, and we don't have time to. Next time we shut the process, maybe we'll take it out and replace it. But right now, nobody's ever done a root cause failure analysis. But you get the idea that stiction is very real, and in the process industries, if you have a safety instrumented system application and a component sits motionless for a long period of time, it might get stuck. And if it gets stuck open and it's tripped to close, that is a dangerous failure mode. Obviously, it's very important then that we understand exactly when and how these various failure mechanisms work. So we started studying stiction to determine the maximum time period before stiction impacts the failure rates. And this, of course, is the maximum time period that one should ever scale cycle test results. What do you think it's going to be? 1 week, 1 month, 1 year? There has been a lot of research done on this stiction phenomena. At Exida, we gathered up expert knowledge. We went out and interviewed maintenance engineers and plant engineers who routinely work on valves. The consensus among the experts was that it absolutely occurs after 1 month or more. There's a lot of information published by O-ring manufacturers. And of course, the stiction phenomena depends on O-ring material and surface finishes of the mechanical parts, and there's a number of variables involved. But what they found for the most part was if a seal, a dynamic mechanical component that had a seal, stayed stationary for between a week and a month, stiction forces will grow. But the delay between cycles plateaued at about 300 hours. So the force required to move goes up and up, and then after about 300 hours, or roughly 2 weeks, it doesn't get any worse. Several experiments were documented in various research studies. Studies on lubrication thickness and magnetic film, thin film disc, equilibrium rest time was measured. Stiction increases and plateaus around 275 hours depending on lubrication type. I don't know about you, but I'm beginning to see a pattern here. In the ISO 13849 functional safety standard for machine safety, they talk about valves must be operated at least once per week or once per shift to ensure the intended function. Now, what we discovered after reviewing all of this research was that stiction becomes significant. And by significant, we mean the forces are approaching the nominal safety factor of the spring in a solenoid valve. Forces become significant 1 week after 1 week, and therefore you never scale cycle test results for more than 275 hours. But thinking about this, we also realized that improvements to safety and reliability could be obtained by cycle testing, especially with solenoid valves. Why? What's going on here? Take a look at this very simplified concept of a solenoid valve. There's typically an electric coil which generates a magnetic field which, let's say, pulls a plunger upwards. The plunger is sealed with typically O-rings or some kind of seal. When the electric coil is de-energized, the magnetic field goes away, the forces from the magnetic field go away, and the plunger falls and blocks process flow. Now, this is not representative of any real designs, and of course, the real designs are far more complex, but there's two important points in the concept here. There are two opposing forces that typically move some mechanical element, some mechanical component in one of two positions. The mechanical component is often sealed with O-rings. This is a situation where stiction would occur. So, in order to really develop an understanding, we focused on solenoid valves for the initial portion of our research. We are fortunate enough to work with quite a few solenoid valve manufacturers, and we interviewed many of them to get their input and to get metrics like what are the typical force vectors involved in your friction, what are the typical forces involved in your springs, how much overdrive or how much safety factor do you put into the excess forces, and how do you overcome the forces of stiction. A couple of manufacturers, one in the UK and one in the United States, were very helpful, providing a lot of detailed design information so that we could precisely model the failure rates caused by stiction. Remember that we said stiction is a dangerous failure mode, and you know if you calculate a PFD average, even using the simplest 1 out of 1 equation, that the probability of failure on demand is primarily a variable of the dangerous failure rate. So this dangerous failure rate is something we really want to look at very carefully, and we want to model very accurately. Now, we also discovered during our research that once stiction is overcome via movement, the bonds creating the binding are destroyed and must reform. In other words, if you keep the parts moving, the stiction forces never have a chance to build up, even with a very small movement. How can we take advantage of that fact? We sat down then and created some relatively accurate models of the dangerous failure rates. In fact, we very much improved the models we were using in our FMEDA methodology. And we classified the dangerous failure rates in a solenoid valve according to 3 categories. Number 1, dangerous failure rates due to stiction. Take a look at that number. Isn't that the majority of the entire dangerous failure rate? I didn't expect that number to be so big. That's very significant. Next category is the dangerous failure rate due to failures that are not due to stiction and that are detectable, typically detectable in a partial stroke or a full stroke test. And lastly, the dangerous failure rates not due to stiction that are really undetectable in a full stroke test. Fortunately, that number is very small. Now let's think about what these numbers mean. If we were able to keep that solenoid moving, and what do I mean by moving? Let's say we move it at least once a week. What would happen to that lambda d stiction? And remember, the bonds that cause the stiction, once the movement overcomes and breaks those bonds, they have to start reforming all over again. What that means is the lambda d stiction goes to 0. I just reduced the dangerous failure rate of the solenoid valve in my application by more than half. That's nice. That's a nice improvement in safety. Take a look at the total dangerous failure rates in case 1, where we don't do any solenoid valve stroke testing. That solenoid valve might sit for years, never moving. And in the particular example we worked up, we did a manual proof test every 2 years. The total dangerous failure rates is nearly 190 fits, or 190 failures per billion hours. In case 2, we did infrequent valve stroke testing, and you can see we still have 190 fits, but a strong majority of those are detectable by measuring pressure output on the solenoid valve during a stroke test. And in a final element assembly, often the solenoid valve does a full stroke, feeding pressure to an actuator, and the actuator does a partial stroke, and so you can implement these tests in such a way that it doesn't impact the process. And you can get some nice improvements in safety with the stroke testing, and we've known that for years, and we modeled that in our Excellentia engineering tool. But what we didn't realize is if you have frequent valve stroke testing, the dangerous failure rate dropped to 86.2 fits. Now, you can still detect most of those, which really means that if you can detect and repair, you've really improved safety. You can see this by looking at the PFD calculations as a function of time. The green line represents PFD, classic increasing PFD, until we get to the 2-year proof test interval. And we did assume perfect proof testing for this simple example. And you can see the PFD average is sitting around 7 times e to the minus 4. Now in case 2, where we do infrequent stroke testing, or partial stroke on the valve, full stroke on the solenoid, we have a substantially lower PFD average, and that assumes, of course, that we are able to detect and repair solenoid valves. But lastly, in case number 3, where we do frequent valve stroke testing, if we cut that dangerous failure rate down, and we still detect most of those failures, we substantially reduce the PFD average. Now, I will say that that blue line in the bottom there is so small we can hardly see it, so let's blow it up a little bit. Even when we amplify the scale, we see the classic sawtooth pattern, and we're running a partial stroke test every week, 168 hours. Our PFD average is sitting down in the 3 times 10 to the minus 6 range, a substantial improvement in safety, at least measured by the PFD. So it's very interesting, this stiction phenomena. We realized that frequent partial stroke testing might be very valuable. And so we're thinking about how to implement a good final element design that takes full advantage of this phenomena. And we recommend implementing automatic or semi-automatic stroke testing in final element designs. Now, if you're going to put in a partial stroke test, you do get a lot of benefit if you run it once a quarter, once every 6 months, even once a month, or in the case of our earlier example, 10 times a year. But We're going to show you that you get we have already showed you that you get significantly much better benefit if you run it once a week, or maybe even more frequently. Make certain, but I've heard a lot of horror stories of partial stroke designs. Designs that cause false trips. And it's absolutely possible to have a bad design and that ends up causing false trips, which end up being turned off and never used. I'm not a plant person. I've really never worked in a plant, but I've been out there for a few weeks at a time, and it was very clear to me working with some of the maintenance people that any product, any safety product that causes false trips will probably be disabled. I remember hearing a production manager come down yelling, "You have shut down our production. How do you expect us to make money if we don't produce? If we don't make money, you don't get paid and you don't have a job." I won't forget that lecture. Make certain, though, therefore, it's important that you make certain to properly design these partial stroke testing subsystems. Make certain that the movement in the actuator valve assemblies is very small. It's okay to do the solenoid with a full stroke, but make sure the actuator doesn't move much, and the valve doesn't move much, so the stroke testing does not cause a process disturbance. You don't want to restrict the flow and start a problem, which may very well result in a trip. Don't let actuator pressure drop too far, as the stiction bonds might let loose. And if the partial stroke tries to restore the pressure, it's too late. I've seen several designs where the partial stroke test box kept dropping the pressure until it saw movement. Well, by the time the stiction bonds break loose, you have too much movement and it's too late to stop and you get a false trip. So I think it's very important not to let the actuator pressure drop too low. Of course, unless there's a real trip. Begin the stroke testing on a weekly basis, taking full advantage of the stiction phenomena, not growing too high. And of course, why wouldn't you run a stroke test more frequently? Well, other than the worry about a false trip during each stroke, and the way to solve that, of course, is to properly design the partial stroke testing scheme. But other than that, there is another reason for not running stroke testing weekly, and that is if you will exceed the maximum cycle ratings of a part. Let's see, if we do a cycle test once a week, it's 52 times a year. Let's say we want to go for a useful life of 10 years, that's 520 cycles. You know, I've looked up a lot of the ratings on a lot of these products, and most of them are sitting at least 100,000, if not 1 million, or sometimes even 10 million cycles. It's very hard for me to believe that products designed for high cycle applications, which is virtually everything on the market today, would have any problem with maximum cycle ratings. However, I did want to warn you and make sure you check that, because we don't want a premature wear out. 500 cycles, no big deal. 1,000 cycles, who cares? They're virtually nothing. After a few months of testing, if the number of times the valve is found, if the valve is found to be stuck a number of times, you better cut the testing period in half, because it means the stiction is building up faster than we thought in your particular application. And you can repeat the testing procedures until the optimal test interval is discovered. It appears to me in some of our initial research that 1 week time is an excellent place, and it would likely stay that way. Now don't forget, you're supposed to be asking questions. I haven't seen nearly enough questions here. So I'm looking. Make sure, type away anytime you want. We believe, therefore, that valve stroke testing can have significant beneficial impacts on safety, and that you can have even more impact than we imagined if you frequently run the stroke test. Full stroke on a solenoid, partial stroke on an actuator valve, especially if the testing is frequently enough to prevent stiction bonding from growing even close to the return force of the various springs. Most beneficial practice is 1 week or more. We believe there is a reduction in the false trip rate as well, but we haven't quite managed, or we haven't finished that yet. Got a question. Thank you so much. I will say the earlier group was a little more lively, but it's getting late in the day in the Eastern time zone and very late in Europe, so I'm very thankful for you folks being awake and paying attention. How do you know if a solenoid is stuck? We are going to have another web seminar coming up probably next month on design options, where we will discuss specific pneumatic and electric circuits for implementing partial stroke testing. But one of those circuits, or one of the best possible testing schemes, is a scheme where you de-energize a solenoid coil, or you lower a pressure with an analog testing box. But the important thing is that you measure actuator pressure and you measure actuator position with an analog transmitter. There are several commercially available test boxes that measure actuator pressure, and not just a position switch, actually measure the pressure. So if you pulse a solenoid, or if you ramp an analog pneumatic device and measure the pressure in the actuator, if the solenoid is stuck, if you de-energize the solenoid and the pressure does not drop, you know the solenoid is stuck. If you see a situation where the pressure drops and the valve does not move, then you have stiction or some other form of binding in the actuator valve assembly. So it's very important, in my opinion, to monitor actuator pressure and valve position as an analog measurement. We're going to get into that in detail in our next web seminar. Another question: why do some certified companies perform cycle testing? Well, cycle testing is a valid method when a product is frequently being used. But of course, in low demand, what we have learned is that you really can't scale. Cycle testing is not a valid method if a product sits motionless for more than a week. And in the process industries, that's common. And so I would have to say that I hope everyone recognizes that the failure rates from this kind of a certificate are absolutely not valid in low-demand process industries. Thanks for the questions. Let me check again. Okay. At the moment, we have all of our questions cleared. I would like to point out that we are going to be having a future web seminar detailing the pneumatic electric circuits, and some of the coverage factors, and doing detailed analysis on a number of different optional partial stroke testing designs. It's absolutely my opinion that the partial stroke testing, if properly implemented, can have a significant impact on safety and even reduce the false trip rates. We're going to have to show you why, because I think some of the earlier designs were very poorly done. They caused false trips and gave the whole concept a very bad name. And it is easier to mess up. It is easy to mess up the design. So we're going to talk about that. Another question that came in. Thank you. Will redundant solenoids help with stiction? And the answer is, well, no. I could install 2 solenoid valves. Now, the interesting thing is, what if you had 2 solenoid valves? You have to ask, does stiction bonding build up at the same rate in both of those solenoid valves? Well, for the most part, I don't know this for certain because I don't have hard data, but I would guess the stiction bonding and the friction forces generated by the stiction bonding will build up in both units at roughly the same rate. So if you let them sit too long, both of those solenoids will have a similar stiction force. And if they are the exact same solenoid valve, if you just put in 2 of the exact same brand or the exact same design, if you have a dangerous failure due to stiction, it's likely to be a common cause failure, and both of the solenoid valves would fail for the same reason at the same time. So not only is stiction a dangerous failure rate, but in redundant designs, it's likely to be a dangerous common cause failure rate, which effectively eliminates the value of the redundancy. I've never been asked that question before. And now it makes me realize that this is even more significant than I thought. Of course, you could put in a single solenoid, and you could run partial stroke testing every week, and as long as your design does not cause an increase in the false trip rate, you may have substantial improvement in safety and save money compared to a redundant solenoid design. I'm going to take some notes about that, and I'm going to add that example to our next web seminar because that was an excellent question. Thanks so much. Please stay tuned for exida web seminars. If you have any questions about stiction, don't hesitate to send Mrs. Stewart an email, lstewart@exida.com, and we'll get back to you with an answer. I see another question coming through, you suggested weekly testing. Isn't the process valve stiction more critical? I assume you mean more critical than the solenoid valve. Good questions. Probably, we haven't finished detailed research on the valve or the actuator yet, but I know that the problem occurs when you have mechanical parts with seals, like a piston actuator, like a rack and pinion actuator or a Scotch yoke actuator, driven by a piston and returned by a spring. These sort of things will definitely have stiction, but if you implement a partial stroke test on the actuator and valve, you can eliminate the stiction in not only the solenoid valve, but the actuator and the valve stem also. We haven't done any detailed FMEDA analysis, and we haven't reviewed this with the actuator and valve manufacturers yet, but we will. We have a lot of research to do yet. I'm excited with our results to date, but we have more to do. Thank you for that question. I will say that if you come up with any more questions, we very much appreciate having your questions and comments. Send us an email, as I said, and stay tuned every Wednesday for the Exida web seminars. Thank you very much for your time today, and I hope you felt your time was well worth it. Stay tuned, and goodbye.